chemical warfare agents, one of my areas of expertise. And I was invited down again this fall to talk about another area that I do in chemistry, one of my research areas, which is on quantum mechanically based computational chemistry. And I put this talk together a number of years ago because I wanted to try to show how computational chemistry can be related to real-world events. And normally when I start off this talk, I like to sort of assess the level of my audience. And so if you would raise your hand, all those who've completed a course in quantum electrodynamics, quantum mechanics, tensor calculus. How about general chemistry? Woo! Okay, and organic chemistry? Okay, well, if you've taken general chemistry and organic chemistry, you should be able to follow what I'm saying. Now, we're going to be looking at some slides, and there's going to be some hairy mathematics on the slide. Don't worry about the mathematics. I'm going to try to explain what the mathematics is telling us. Okay? So we're going to try to keep it as qualitative as possible. All right? You don't have to worry about the quantitative part. All right? So the talk is entitled Quantum Mechanics of Hot Peppers, Chemistry on a Silicon Chip. Now, hot peppers, and if you look at the left side of the slide, sometimes hot peppers can be really hot. The chemical substance that makes hot peppers hot is a substance called capsaicin. And capsaicin has the structure shown here. This is a space-filling model of the capsaicin molecule. All right, we're going to be looking at the nature of capsaicin. And we're going to try to set up an everyday experience. So how can we use quantum mechanics to learn about the everyday world? So let's take a typical example. Maybe this has happened to you tonight. You're at your favorite Mexican restaurant. You eat several hot peppers. I know when I was a college student, it used to be the big macho thing to try to eat more hot peppers than your buddies. Okay, yeah, muy macho, sort of thing. So you're eating your hot peppers when suddenly it hits you. Okay? Arg. Your mouth is burning and red hot. You reach for your favorite beverage, but only if you're 21. Okay? And you take a long drink of your favorite beverage, but nothing. It doesn't do a thing. Whether you're drinking beer or water, it doesn't seem to take away the heat. Your mouth is still on fire. So, in desperation, there's some sour cream or some guacamole on your plate. Or maybe you have a glass of milk. You eat the sour cream or guacamole or drink the glass of milk, and you get a little bit of relief. Okay, what is it that's taking place? So you begin to ask yourself, what gives? Why doesn't the water wash away the hot peppers and cool off my mouth? Or you might even begin to ask yourself, what is it in the sour cream or the milk or the guacamole that counteracts the hot peppers, that seems to counteract the hot pepper? Well, to answer this, it's time to start thinking like a chemist. Okay? That's what we're going to try to do right now. Well, if you've taken general chemistry, and certainly if you've taken organic chemistry, in the lab, you've heard of this expression, like dissolves like. Okay? This is a pretty simple adage that's used by chemists all the time, and it can be used to explain a number of things, but one of the things it can be used to explain is why I wasn't able to scrub away the grease stain on these particular pants when I accidentally spilled a slice of pizza, pepperoni pizza, on them a few months ago. All right? Water did not take away the grease. And we sort of know that from our everyday experience. Well, when we look at this concept of like dissolves like, it's based on what we call chemical affinity. And chemical affinity says that substances with certain properties, similar properties, will readily dissolve in one another. Okay? So the pizza grease that was on my pants is not like water. It's dissimilar from water, doesn't have the same type of properties as water, and so it will not dissolve in water and be washed away. So the question is, how does this apply to hot peppers? Well, when we tried to wash away the hot pepper pain-causing stuff, okay, water didn't do it, but the guacamole did. So obviously, the hot pepper pain-causing stuff is going to be more similar to the chemical substance that are in the sour cream or the milk or the guacamole than they are to water. Okay, what happens is that the hot pepper pain-causing stuff dissolves into the milk, the sour cream, the guacamole, and when we swallow, it's removed from the lining of our mouth. Now, our mouth has the sensors, the sensory neurons that detect the presence of the hot pepper pain-causing stuff, and our stomach doesn't. So, even though it's in our stomach, it's not causing the pain. Okay, so what we want to do is we want to look at the chemical makeup of the hot pepper pain-causing stuff, water, and the components that are in sour cream, guacamole, or milk. Okay? Well, in the hot peppers, as I said at the very start on the slide, the active ingredient in the hot peppers, that's what's compound that is responsible for the heat, is a substance called capsaicin. Well, in our favorite liquid beverage, well, we're looking at mostly water. Okay? And finally, in the guacamole or the dairy products, we're talking about fats, such as fatty acids and esters. And these are major components of guacamole or dairy products. Now, these fats and fatty esters are called lipids. Okay, so we want to look at some of the different compounds, the actual compounds. So let's look at capsaicin first. When we look at capsaicin, if you've taken organic now, you should be able to recognize some of these functional groups. We have an aromatic ring with a hydroxy group, so it's a phenol. We have an amide functional group, but we also have this hydrocarbon tail here. Okay? Here is a model of the lowest energy conformation of capsaicin here. Right? So that's a ball and spoke model, and there's our structure right there. So that's the molecule capsaicin. That's the hot pepper pain-causing stuff. Well, let's look at some of the lipids. We all know what water looks like, all right? Or we should know at this point what water looks like. So let's look at some of the lipids, okay? And one common lipid, oleic acid, which is found in guacamole. This is a cis monounsaturated fat. Okay? This is its chemical structure here. If we notice that oleic acid has an acid functional group, this is a polar functional group for those who've taken organic chemistry, and it has this long hydrocarbon tail here, and that long hydrocarbon tail is nonpolar. Okay? And again, here's our ball and spoke model for oleic acid. Another common fatty acid is palmitic acid. Now, palmitic acid gets its name because it was isolated from palm plants, but palmitic acid is also found to a very high extent in avocado, and that's what guacamole is made up of. And palmitic acid is a saturated fat, so you probably heard that eating a lot of avocado and guacamole isn't good for you because it contains the saturated fats, just like animal products. Okay, again, we have a polar hydrocarbon head and this nonpolar hydrocarbon tail. And finally, one of the fats in dairy products is acetic acid, which is a trans monounsaturated fat, has this structure right here. And again, polar acid head, nonpolar hydrocarbon tail for all of these fatty acids. These are very common types of fats that are found in the substances like guacamole, sour cream. So we want to ask ourselves, in what way is capsaicin similar to these fats and dissimilar to water? So let's look at some of the ways we could compare them. Well, certainly their size. All right? We know that capsaicin and those fatty acids are fairly large molecules, where water itself is quite small. Okay, so maybe they're dissimilar or similar in terms of their size or in their mass. Okay, that's sort of a corollary to their size. Capsaicin and the fatty acids are much heavier molecules than water, so maybe that's where they're dissimilar. Obviously, chemical formula, we know that they're different in terms of the chemical formula. And finally, their structure. Okay, they are dissimilar in terms of their structure. So what we would like to do is to try to come up with a way that we can explain the similarities between capsaicin and the fatty acids and the dissimilarity between capsaicin and water. Okay? So is there a tool which will allow us to compare these three different compounds? And there is a tool that's been developed over the last 50 years. It's called computational chemistry. And in computational chemistry, we're going to use computers to solve the quantum mechanical equations which describe the behavior of atoms and molecules. And in particular, computational chemistry has become very important in the last 20 years because computational chemistry involves a lot of computer work, okay? A lot of computational effort. And computers have become faster and faster and faster over the last 20 years. So today, I started doing computational chemistry in the late 1970s. It was all done on mainframes, and we would sit at essentially teletype machines and communicate with a mainframe. And the mainframe would do calculations over days. And then we'd go pick up our results. And today, the same type of calculations that took me days to do can be done on a typical desktop PC in probably 10-15 seconds. I've done the same experiment. I took the calculation that I did as a grad student and did it on a PC, and it took about 15 seconds. Okay, so computational chemistry, big area. So let's talk about computational molecular modeling, and this is where it comes in on chemistry on a silicon chip. So molecular modeling gives chemical results which are based on mathematical models which describe the behavior of atoms and molecules. And it was recognized a long time ago that mathematically based models could be very good at describing chemistry. So we have this quote here: the more progress physical sciences make, the more they tend to enter the domain of mathematics, which is a kind of center to which they all converge. We may even judge the degree of perfection to which a science has arrived by the facility with which it may be submitted to calculation. Well, if we take that last sentence of this quote, the perfection of science, we find that chemistry now is a perfect science because we can virtually answer every question that we could pose as a chemist by mathematical modeling. This was a quote that was made over 100 years ago by a Belgian mathematician. His name was Adolphe Quetelet. Now, the molecular models we're going to be using are based on the mathematics of quantum mechanics. Quantum mechanics is a relatively new science. It's only about 100 years old at this point in time. And we have a quote here by one of the founders of quantum mechanics: the underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known, and the difficulty is only that the exact application of these laws leads to equations much too complicated to be soluble. Well, this was a statement made by Paul Dirac, an English physicist, back in 1931. He's been more or less proven wrong in a sense. notice that he says the difficulty is only that the exact application of these laws leads to equations which are much too complicated to be soluble. And so what we're going to find is that rather than trying to come up with exact solutions to these equations, we're going to come up with approximate solutions to these equations. And for us as chemists, it's these approximate solutions which are good enough. They tell us everything we need to know. Okay, now molecular modeling is based on quantum mechanics, and this is going to allow, as I said before, chemists to predict the behavior of molecules before they're even made. Now, as chemists, when we use quantum mechanics, we're interested in electrons. All right? We know that when we make chemical bonds, in particular covalent bonds, they involve electrons. And they involve specific types of electrons. They involve valence electrons. And so computational-based chemistry looks at the nature of the electrons that are in a molecule. And so what do we want to do? We want to know two things. We want to know the location of the electrons. Where are they located in the molecule? And we want to know the energy of those electrons. Okay? So knowing the location is going to allow us to determine the structure of the molecule. All right? And knowing the energy of the electrons is going to allow us to determine thermodynamic parameters such as bond strengths. Okay, so those are the kind of things that chemists want to know. Where are the electrons in a molecule? Because that tells us the structure. And what are the energy of those electrons? Now, we know that when we make covalent bonds, all right, the location of the two electrons in the covalent bond sort of determines the overall structure of the molecule we're looking at. So let's look at a simple general chemistry problem or an first semester organic chemistry problem where we're using ways of keeping track of the electrons we call Lewis structures. All right? And many of you will recognize this is a Lewis structure for a carbon atom. It shows the 4 valence electrons of the carbon atom. This is a Lewis structure for the hydrogen atom. It shows the 1 valence electron of the hydrogen atom. When we make the molecule of methane, okay, carbon atom contributes 4 valence electrons, each hydrogen 1 valence electron. We're going to make 4 covalent bonds in which we have a sharing of electrons, hence the covalent bond, between the carbon nuclei and each one of the 4 hydrogen nuclei. All right, so we learn about that in organic and also in general chemistry. So this tells us how the valence electrons are going to dispose of themselves in 4 covalent bonds. Now, one thing that the Lewis structure doesn't tell us, and that is it doesn't tell us the shape of the methane molecule. Now, if we were to look at the methane molecule just from this sort of Lewis structure, which is sort of a naive way of looking at it, you might think that methane is a square planar molecule. Is methane a square planar molecule? How about you organic folks? No, it's not. Okay? We know it's not. Okay? How do we know it's not? Well, we have one theory that allows us to sort of predict the shape of the molecule. And the one theory that allows us to predict the shape of the molecule is based upon the number of bonding or non-bonding pairs we have around a central atom. Okay? What's the name of that theory that allows us to predict the shape of the molecule? Does that help? Valence shell, electron, pair, repulsion model. Okay? The valence shell electron pair repulsion model is a qualitative model. Okay? It's not mathematically based. It is based on physical reality. Okay? And it's based on the physical reality that pairs of electrons are going to repel one another. Okay? Like charges repel. When you have pairs of electrons around a central nucleus, they're going to want to try to get as far apart from one another as possible. And depending upon the number of bonding or non-bonding pairs you have, you're going to take on a particular structure. Well, in that model of Lewis structure of methane, we had how many bonding pairs? We had 4 bonding pairs. And when you have 4 bonding pairs, anybody know the structure that you're going to get?
Tetrahedral.
It's got to be tetrahedral. There it is right there. So there's our tetrahedral methane right there. We've used a model to predict the structure of methane. Now again, this is a non-mathematical model, but it is based on physical reality. Okay? Now in quantum mechanics, we're going to go down to what we call first principles. And we're going to use the first principles as to the behavior of molecules, which can be well defined by mathematical equations. And we're going to use those mathematical equations to build a picture where the electrons are in a molecule. Okay? Now, quantum mechanics, when you look at a Physical Chem 1, Physical Chemistry 2 textbook or a physics textbook, and they introduce you to quantum mechanics, one of the equations that they always show you is this very deceptively simple looking equation right here. H psi equals E psi. This equation was first developed in 1926, 1927 by a German physicist. His name was Erwin Schrodinger, and so this is called the Schrodinger wave equation. Now, this deceptively simple looking equation here is really just a shorthand. Okay? So like a lot of shorthand we have in science, there's a much more complex underpinning besides this simple equation. Okay? And we'll look at it in a little bit more detail. Now, all of quantum mechanics comes about from our attempts to solve the Schrodinger equation for the interaction of electrons and nuclei within a molecule. Okay? Now, when we look at this expression H psi equals E psi, we see this sort of Greek symbol psi and psi. That Greek symbol psi represents something we call a wave function. Now, a wave function is a mathematical equation. Oops. I'm backwards here. Okay, that wave function is a mathematical equation that contains all of the information about electrons in a molecule. Okay? It's locked away in this function. Now, it's called a wave function because when we're dealing with matter at the quantum level, like an electron, electrons behave like waves. Okay? And so the function itself has a wave-like nature. For example, if we were to look at a wave function, it would contain sine and cosine components. And we know that sines and cosines are used to describe wave functions. Okay? Now, locked within the wave function, as I said, is all of the information. And to get that information out of the wave function, we have to ask questions. Okay? And so the symbol H here stands for what we call an operator, a mathematical operator. A mathematical operator simply asks the wave function a question. Now, the mathematical operation H is called the Hamiltonian Operator. It's named after an English physicist who developed a set of equations of motion. And the Hamiltonian Operator, when applied to the wave function, asks questions about energy. In particular, it asks questions about the energy of electrons. Okay? And so this component right here is the answer, the energy answer. And so the wave function is like an oracle. If you've taken any mythology, you might have heard of the Oracle of Delphi. The Oracle of Delphi was a woman who knew the answers to everything, could predict the future. And you would go and ask the Oracle of Delphi a question. And you had to be very careful in how you asked the question. Okay? But if you ask the question in the right way, you'd get an answer back. And so let's think of the Schrodinger wave equation as a way of asking the oracle information about the energy of electrons. Okay, H psi equals E psi. Now, this particular type of equation belongs to a class of mathematical functions called an eigenfunction. Now, an eigenfunction means something very simple. Okay? In an eigenfunction, we take the wave function, we ask a question of it according to the operator, and we get the answer back as a numerical value, what we call a scalar, times the wave function again. Okay? So here's the answer here. Okay? And this is called the eigenvalue. So an eigenfunction, when operated on by an operator, gives you the eigenvalue, and the eigenvalue is E, the energy of electrons. Okay? I'm just going to give you a simple example. Anybody take Calc 1? Okay, so Calc 1, you've seen differentiation. Okay? Here's a simple differentiation, which is an example of an eigenfunction. Okay? Let's take this equation right here. What we want to do is we want to find a function, okay, such that if we take the first differential of that function with respect to x, we get a numerical value back times that function again. Okay? And so when we talk about solving the eigenfunction, what we're looking for is the correct type of function that goes in here that would give us, that would satisfy this relationship. Now again, we're trying to take the first differential with respect to x of this function, and we want to get the answer, which is a numerical value times the function again. Does anybody know what type of function satisfies this relationship? How about phi equals e to the bx? Okay, if we take the first differential of phi, which is differential of e to the bx over dx, we get this answer right here, b e to the bx, where b is a numerical value. So this is an example of an eigenfunction. You simply get a numerical value times the function again. And if we get that numerical value, and one other important point, in that not every function is a solution to an eigenvalue equation. Okay? Only certain types of functions are. Typically, exponential functions of this type are going to be solutions to an eigenvalue equation. Oops. Okay. So, let's see where we're at. The Schrodinger equation, we've got a wave function. The wave function is an eigenfunction. It's going to get, when we apply an operator on it, it's going to give us back the function again with a numerical value. Let's talk about that Hamiltonian. This is the operator. It's going to do something on that original function to get the answer. Okay? And the hydrogen atom was first studied 100 years ago. And it was found that we could get all of the answers for the hydrogen atom exactly. And here is the Schrodinger equation sort of expanded out for the hydrogen atom. Okay, so the H, the Hamiltonian operator, what is it? Well, it's a bunch of constants, and then it's got a term here. We call that del. I didn't write it out, but that's simply double differential. Again, if you've taken Calc 1, you know what a double differential is. It's a double differential over x, y, and z coordinates times the wave function plus another term times the wave function. Well, this part of the wave function here tells us about the kinetic energy of the electron. It's called the kinetic energy operator. This part of the equation here tells us about the potential energy of the electron. It's called the potential energy operator. The sum of those terms, when we add it together, is the total energy of the electron. That's this value over here. So using this equation, Yeah, it's a little bit more complex than what we saw for the simple representation of the Schrodinger equation, but this still is a type of mathematical equation that can be done by hand, and it was done by hand 100 years ago. Okay? And from it, they were able to determine exactly the energy levels of the electrons for a hydrogen. We could determine all of the different energy levels, getting the exact energies, applying this process. So complex, but not so complex that you couldn't do it by hand. Okay, and again, the takeaway part here is, here's our wave function. Our wave function contains all of the information about the electron in the hydrogen atom. Okay, here's our kinetic energy operator. When this operates on the wave function, we get the kinetic energy. This V here is the potential energy operator. When it operates on the wave function, we get the potential energy, and the sum of those gives us the total energy as a numerical value times the wave function. And so we can just do a simple mathematical process to get the energy out. Okay? So once a correct form of the wave function has been determined, we can use a mathematical expression to factor out the energy. So we can get the energy of the electron, of a hydrogen atom. Hydrogen atom has one electron. Now, what do we know about the hydrogen atom? It has one electron, but that one electron can be in different orbitals, right? It can be in S-type orbitals, can be P-type orbitals, can be D-type orbitals. Those orbitals can have different energy levels, all right? Quantum level 1, quantum level 2, quantum level 3, and so on. Okay, so what we find is that we have to use different wave functions to describe the different orbitals. And so our wave function here is given by this expression where, depending upon the coefficients we've put in here, here, and here, we would have our familiar S, P, D, and F type orbitals. So the wave function, if we look at it, is an exponential type function. We can use that exponential type function to describe the wave function of our electrons. And depending upon the different coefficients here, here, and here, we would get the different shapes of our orbitals. So this is called the radial function here for the hydrogen atom. Okay, now the hydrogen atom is a pretty simple system. It has a single nucleus, it has a single electron. When we're dealing with more complex systems, what we find is that the complexity of the Schrodinger equation expands significantly. It becomes very complex. And in addition to becoming very complex, when we have more than one electron, there is now a new mathematical problem, and that new mathematical problem is at present unsolvable. Okay? So here's an example of an equation that's going to strike fear into the hearts of a quantum chemist. Okay? This is now sort of the expanded Hamiltonian for a multi-nuclear, multi-electron molecule. Okay? And when we look at it, it's composed of a nuclear kinetic energy term, it's composed of electron kinetic energy terms, it's composed of nuclear electron potential terms. We know that there's an attractive force between the positively charged nucleus and the negatively charged electron. There's a term here for the nuclear potential term. We know that nuclei have positive charges. They tend to repel one another. Okay, now we have one of these for each type of particle, for every nucleus, for every electron. Okay, so this starts to get very complex very quickly. Even still, we could solve it except for this last part right here. This is called the Electron-Electron Potential term. So once you get more than one electron in your system, the Electron-Electron Potential term blows up in your face. Okay? And it's this last term that makes it impossible to have what we call an exact solution for the Schrodinger equation for a multi-electron atom or molecule. Okay? We call this electron-electron repulsion. And the reason why we can't solve this last equation has to do with the way we do mathematics. Okay? Let me show you on an example here. We have what we call the three-body problem. Anybody take a physics class where they talk about the gravitational three-body problem? Okay? Well, we also have an electronic three-body problem when it comes to quantum mechanics. Okay. And the three-body problem comes about because we're not God. And we can't do two things at the same time. Okay? One of the things we need to do when we have a system is to determine the relative position of a nucleus and an electron. So we do this in the hydrogen atom. And it's easy in the hydrogen atom because we assume that the nucleus is going to be at the very center of our three-coordinate axis system. Okay? And so all we have to do to determine the interaction between the nucleus and the electron is to determine the position of the electron, which we can do. Okay? We could use its position in XYZ coordinates, or we could use its position in polar coordinates. Okay? But we can specify the position of a single electron with respect to the nucleus at a given instant. All right? Now here's the problem with what we call a three-body problem. We need to know three different things. We need to know the interaction between one electron on the nucleus. We need to know the interaction between the other electron on the nucleus. And we need to know the interaction between the two electrons. Now here's how we do it. We first look at the position of the first electron and we measure the interaction to the nucleus. Then we look at the position of the second electron and we measure its interaction to the nucleus. Okay, here's where the problem comes in. What do we know about electrons around the nucleus? Are they fixed? Do they stay in one spot? No, they're in constant random motion. Okay? So we fixed the position of this electron and we measured it and we have an interaction with the nucleus. Then we look at this one and we look at its interaction with the nucleus. Now we come back to this one because we want to look at this interaction and what's happened to this electron. It's moved from where it originally was. Okay? So in order to solve this problem, we have to be able to simultaneously fix the position of two electrons, which we can't do. Okay? We can only fix their positions sequentially. So fix the position of one, then we fix the position of the other, by which time we go back to the first one and it's moved away. So we cannot determine electron-electron repulsion. Now, hopefully you understand from valence shell electron repulsion theory that electron repulsion is a big deal. Okay? If it's able to predict the shape of a molecule, electron-electron repulsion has a big effect on the energy of electrons. And we can't calculate it exactly. So we can't do what we call an exact solution to the Schrodinger equation. And so this is the problem that chemists and physicists were at 75 years ago. They could do hydrogen atoms accurately. They couldn't do anything else. They couldn't even come close because electron-electron repulsion is so important. So the question is, how can we make quantum mechanics work in the real world? And the answer is, we need to simplify and approximate. Okay? So over 50 years, physicists were coming up with methods to simplify the Schrodinger equation and to come up with approximate methods. Okay? So that we could get around that electron-electron repulsion problem. Okay, so we're going to look at some of these simplifications and approximations. Now, they have a downside. Okay, and that the simplifications and approximations give us only an approximately correct answer as to the electron position and as to its energy. Okay, it's not an exact answer, and it's an approximate answer. But here's the upside, and that is close is good enough most of the time. So by using these simplifications and approximations, we can get a fairly simple answer. Okay, first approximation is called von Oppenheimer approximation. It's very simple. It tells us that the mass of a nucleus is much greater than the mass of an electron. Everybody agree with me? Okay, you learn in general chemistry that nucleus is much heavier than an electron. So we go to this first term, the nuclear kinetic term, and notice that it has a mass term here. That's the mass of a nucleus. If this is very large, this overall term gets very small, and so we can throw it out. Okay? So we don't have to worry about the mass of the nuclei that the electrons are moving around. That's called the von Oppenheimer approximation. The other type of approximation we use is called the Hartree-Fock approximation. Now, in a nutshell, the Hartree-Fock approximation says we're not even going to try to calculate individual electron-electron repulsions. We can't do it, so we're not even going to try. But what we're going to do is we're going to look at the interaction of an electron with the average distribution of all of the remaining electrons. Okay? Now we can come up with an average distribution of all of the remaining electrons. That's fairly easy. So we look at the interaction of a single electron with that. Okay? And essentially by using the Hartree-Fock approximation, we can do away with this term right here. And that's the term that's unsolvable. So that's our approximation. Okay, it's called the Hartree-Fock approximation. So we've cut out two of the terms. We've made this calculation much more doable. Now the first two terms deal with the Hamiltonian. We're simplifying the Hamiltonian, making the computation easier. Now the next approximation is the one that's going to come up with an approximation of the wave function. Remember we said the wave function is a mathematical function that contains all of the information we need to know about the electron. We just have to ask it the right questions. We have to ask it the Hamiltonian operator, and it will give us the energy. So we need to come up with a way of approximating the wave function. And the way we approximate the wave function is we take what we call a linear combination of atomic orbitals. Now what is a linear combination of atomic orbitals? Well, we know that around every type of atom are different types of orbitals. 1s orbital, 2s orbital, 2p orbitals. There are 3 of those, 3s orbitals, 3p's, 3d's. Okay? All of these individual type orbitals can be described by a mathematical function. And I showed you the mathematical function earlier. Okay? So what we're going to say is when we look at the overall molecular orbital, it's made up of a combination of the s, p, d, or f type orbitals that are on the individual atoms. It's what we call a linear combination. Well, that makes sense. So when you do hybridization, okay, you know that a hybridized orbital is made up of a combination of s and p type orbitals. When we're dealing with a molecular orbital, the wave function that describes the molecular orbital is made up of a combination of the s, p, d, and f type orbitals on the different atoms. And it has a mathematical function here. So this is the wave function describing the electrons in the molecule. It is a sum of all of the individual atomic orbitals. Now, those individual atomic orbitals are weighted in various ways. This C term here is a weighting factor. Okay, so when we look at the molecular orbital, it could be made up of 1s orbitals of a particular weighting factor. It could be made up of 2s and 2p orbitals of a particular weighting factor. Okay, so the functions that describe the individual atomic orbitals are relatively simple functions. We're just going to combine and add together all of these relatively simple functions. Okay. So again, these are the relatively simple functions that will describe an S, P, D, or F type orbital, depending upon these coefficients here. If it's an X, it's going to be an S-type orbital, X. And if these are zeros, it would be like an S-type orbital, and so on. So we'll have a large combination of these type orbitals. Those are called the basis functions that make up the molecular wave function psi right here. So essentially what we call solving the Schrodinger equation, what we need to do is we need to find the correct combination of atomic orbitals that describes the molecule. Okay? What we find is that as we find the correct combination of the atomic orbitals, what we have to do is find the weighting coefficients here, the weighting factors. So that's essentially what solving the Schrodinger equation for the wave function is finding the correct combination of atomic orbitals with the correct weighting functions. And we have a relatively simple rule that allows us to determine when we found the correct wave function. And this is called the variational principle. Okay? And the variational principle is the key theorem in quantum mechanics that tells us that the Eigen Value E obtained using the approximations must always be higher in energy than the actual value. So all of the simplifications and approximations that we've made results in an energy that's always higher in energy than the actual value. Now that might not sound very useful until you think about it this way. That gives us a target to reach for. We know that anything that we do to our wave function, any of the changes of coefficient that we make to our wave function, if they result in a lower energy, are moving in the correct direction. So we start off with what we call a guess wave function. We combine atomic orbitals, and we use a certain set of coefficients to combine them with. And we carry out a Schrodinger equation on it. We apply the Hamiltonian to this combination of atomic orbitals, and we get an energy value. Then we can change the coefficients. And we do the Hamiltonian again. We apply the Hamiltonian to our modified wave function, where we've changed the coefficients of the wave function. And we got another energy. Well, if the second energy we got is lower in energy than the first one we obtained, because of the variation principle, that tells us we're moving our coefficients in the correct direction. So we take our combination of atomic orbitals, our S, P, D, F orbitals on the different atoms, and we combine them using different weighting coefficients. That gives us a wave function. We apply the Hamiltonian to it. We get the energy. And every time the energy goes down, that tells us that we've moved the coefficients in the proper direction. So we keep doing this until we don't see a change in energy anymore. Okay? When the energy reaches its absolute lowest value that we can get, that value is still going to be higher than the actual energy, but it's as low as we can get using the modeling technique that we're using. At that point, we have come up with the best wave function for that molecule. Now, the wave function tells us where the electrons are. So at that point, we know where the electrons are because we have the wave function for that molecule. And we also have the energy for the electrons. So we know the energy of the molecule at that point. Okay, so what I've just talked about is called an iterative process. Iterative process means you cycle through a series of calculations until you reach an endpoint. Okay? And one thing that computers are really good at, and that is carrying out repetitive, iterative processes. And so what we have here is a little flow chart that tells what's occurring when we do a calculational process. Now, there's software out there today that has been written to allow chemists who are not experts in doing computational molecular modeling. It allows them to do the types of modeling that would have taken a professional theoretician to do 20 years ago. Okay? And essentially, what you do is, on a computer screen, you input an initial structure. And you actually have a little model kit. In most of the software packages, they have a little model kit. You want a tetrahedral carbon, you put in a tetrahedral carbon. You want an sp2 carbon, you put in an sp2 carbon. You build your model. Okay? And that is your initial structure. Now, the computer does this for you. It looks at your initial structure and it determines what's called a guess wave function. It says to have a structure like you have inputted, we're going to take this particular carbon 1s orbital and we're going to assign this weighting factor, this coefficient. We're going to take this other carbon, sp2 orbital, we're going to assign this weighting coefficient. Okay, so it builds your guess wave function for you automatically. Okay, so here's our guess wave function. What it's doing is it's picking the atomic orbitals that it's going to need, and it picks weighting factors that it's going to need to come up with the guess wave function right here. Okay, then it's going to apply the Schrodinger equation. Essentially, it's going to take the Hamiltonian operator. The Hamiltonian operator operates or works on the wave function, and you're going to get out the Eigen Value, which is the energy. So it's going to determine E. Now, once it's done that with the guess wave function, it's then going to change the coefficients. Okay? And it has an algorithm that helps it to predict how it's going to change the coefficients. But it's going to change the coefficient. Okay? And once it's changed the coefficient, it's then going to do the Schrodinger equation on that new wave function. Okay? And it's going to determine the energy. And it's going to compare the energy that it gets the second time with the energy that it gets the first time. If the energy is lower, it goes, great, continue to move the coefficients in such fashion. If the energy is higher, it says, that was a bad change. We're going to try changing it this way. And so what it does is it cycles through this process over and over and over and over and over again. And generally it takes maybe from 25 to thousands of cycles. Okay? Either way, it happens very, very quickly with a fast computer. Okay? And eventually it reaches a minimum energy. It can't get any lower. At that point, when it reaches the minimum energy, the calculation is finished. At that point, you have a wave function which accurately describes where the electrons are in the molecule. Okay? So, once we know where the electrons are, we can then get additional information. So, let's look at a system, a very simple system, if we're told where the electrons are. Okay, and this molecule right here is HCl. Now, I think if you've taken organic chemistry, and quite possibly general chemistry, you should realize that when you have a hydrogen bonded to a chlorine by a covalent bond, that bond is what we call a polar covalent bond. Okay, the electrons are not shared equally between the two. Chlorine, being more electronegative, gets more than its share of the electrons. Hydrogen gets less than its share of electrons. The molecular orbital calculation would determine this information. We know it from our sort of qualitative understanding that those electrons are not shared equally, but computational chemistry would determine it from first principles. And so what that means is that since the chlorine here gets a little bit more than its share of electrons, it has a negative charge in the region of the chlorine atom. And since the hydrogen atom gets less than its share of the electrons, it has a positive charge around the region of the hydrogen within HCl as a whole. Now, once we've determined where the electrons are, a little bit more electrons are on the chlorine, a little bit less electrons are on the hydrogen, we can do something called electrostatic mapping. This is where we're going to get a picture of the relative electron density in the molecule. And to do what we call electrostatic mapping, the computer says we're going to pick what we call a point positive charge. And we're going to place that point positive charge a specific distance from the surface of the chlorine and from the surface of the hydrogen. And we're going to do that all around the molecule. Now, a point positive charge and a negatively charged region of the molecule, like around chlorine, that type of an interaction, positive and negative interaction, is an attractive interaction. Okay? And we're going to map attractive interactions by a color. So when you see the color red, that means you have a negative region to your molecule because the point positive charge that we're using to do electrostatic mapping is interacting with it in an attractive way. Now, on the other hand, in electrostatic mapping, if we bring a point positive charge that exact same distance to the surface of an atom that has a positive charge, like the hydrogen here, now we have a plus-plus interaction. That's a repulsive interaction. Okay? And we're going to map anywhere that has a repulsive interaction as blue. So, in what we call electrostatic mapping, we're going to look at the surface of the molecule. And where we see red, that means we have negative charge in the molecule. Where we see blue, that means we have positive charge in the molecule. Now, what would neutral color be? Well, what do you get when you mix red and blue? Well, you get orange, but we're going to use green as our neutral color. Okay? We're going to use green as our neutral color. So wherever you see it green, it's more or less electrically neutral. There's not an excess of charge there. Okay, so I was going to do an actual example of a calculation for you. My PC laptop failed on me, and it's not a Mac software. But what I did was I set up these calculations. They took a very short time to do, and now we're going to get the results of a calculation. Remember what we set out to try to prove. We're trying to prove in what way is capsaicin similar to the lipids and dissimilar from water. Okay, and we use quantum mechanics, which I sort of talked about. I told you how quantum mechanics, number one, it finds where the electrons are by solving the wave function. And here are the different structures right here. Here is capsaicin. Now you notice overall the color of capsaicin is pretty green. Okay? By the aromatic ring, by this hydrocarbon tail. It does have regions of positive charge. Here we have a hydrogen bonded to a nitrogen. Notice how it's blue there. That hydrogen is positively charged. It has regions of negative charge. Here we have an oxygen atom, These are typically electronegative atoms. These are slightly negative charged. So there is, and here's an oxygen atom back here. That would be red color back here, but we can't see it. But when we look at capsaicin, what we see is that, by and large, the surface of a capsaicin molecule is more or less neutral. It's not highly charged. It is nonpolar. Okay? We see this now unambiguously. For the most part, capsaicin molecule is nonpolar. Yeah, it has a couple of small regions of charge, but most of the molecule is nonpolar. Here's water. Did the same thing for water. Okay. Now, when we look at water, we see that the region up here around the oxygen is red. That tells us that this part of the molecule, the oxygen, has a large excess of negative charge. When we look at this part down here, where the hydrogens are, we see that the water molecule is blue. Intense blue, that means that those hydrogens have a strong positive charge. So this electrostatic mapping for water now tells us what we learned in general chemistry and organic, that water is a polar molecule. Okay? So capsaicin, nonpolar, water polar. Let's look at some of our lipids. Okay, when we look again at the lipids, we see that, yeah, there is a region of the fatty acid, oleic acid, which is polar because it has intense blue and intense red, but by and large, most of the molecule here is nonpolar. It's mostly neutral. Okay? And again, we see that for the other molecules. We can put them all on the same screen right here. So we've used quantum mechanics to find out where the electrons are in these various molecules. Once we know where the electrons are, we can do an electrostatic mapping. This is going to tell us, are the molecules polar or are they nonpolar? So this brings us back to the original statement chemists say. Like dissolves like. What is the property that we're looking at when we talk about like dissolves like? Is it the size of the molecule? No. Is it the shape of the molecule? No. It's what? The charge, or the polar, nonpolar nature of the molecule. Okay? So most of you, if you take general chemistry, should remember that. But here we've used quantum mechanics to give us this information, more or less in a graphical way. Okay? So what is the take-home from this talk? Well, the take-home isn't that you need to remember all of the different approximations and simplifications that we use to make quantum mechanics useful as chemists. Okay? The take-home is that computational molecular modeling is just another tool that chemists can use to get information about molecules. Okay? And it's a very useful information. And it's a skill that, if anybody is planning on becoming a practicing chemist, it's a skill that you need to have. If you're going to go on to graduate school, it's a skill that you need to have. If you're a biologist, if you're thinking about going into certain types of bioinformatics, okay, it's a skill that you need to have, being able to do computational modeling. Okay? And so that essentially wraps up my talk at this point. I appreciate you for sitting there and listening to this. And if anybody has any questions. Yeah?
The energy approaches zero eventually. It's not negative ever, right?
Yeah, the energy is never zero. Well, it's negative. Well, there's two different energies. If you're looking at the overall energy of the molecule, that energy can be negative because it's essentially like the heat of formation. So if you're looking at the heat of formation, some of those can be negative. But the energy we get from this type of calculation is always higher than the actual energy.
Okay.
Okay. Any other questions? Yeah.
So why don't we quiet down a little bit so we can hear questions?
Yeah. You said at least we can predict the distance between an electron and a hydrogen atom, right? At least we can do that for hydrogen.
Yeah, we can predict the energy of the electrons.
What do we use to tell us where the electron is? What do you use to freeze what you say, just freeze it in time?
Okay. What tells us where the electrons are the wave function. So we have these simple equations for the wave function of the hydrogen atom. All right? And that tells us where the electrons are around the hydrogen atom. And then we can determine what would be the energy of the electron in that wave function, in that orbit.
So if that's in theory, but if I have an actual hydrogen atom in this, my friend has another one, they would have their electrons in different positions.
Yeah, they would have electrons instantaneously in any random position within a certain volume of space that would correspond to the 1s orbital for the hydrogen. But it could be anywhere in there, right? But you know that your electron is going to be in the 1s orbital, and the other person's electron is going to be in the 1s orbital, okay? Any other questions? All right, well, thanks a lot.